Hey everyone, and welcome! Today we're going to pull back the curtain on a really clever data structure called the heap. Now at first glance it looks like a tree, but its real genius is its disguise. It's actually one of the simplest things you can imagine, and that's exactly what makes it so incredibly powerful.
But before we get into the nuts and bolts, let me ask you something. What could possibly connect the way your computer decides which program gets to run next, the algorithm that finds the absolute fastest route on a map, and the way we shrink files down to save space? It sounds random, right? But the answer is a single, elegant data structure.
Okay, first things first. We have to clear something up, because if you've done any programming, you've probably run into the word heap before, but it's used for two totally different concepts.
On one side, you've got heap memory. That big, kind of chaotic pool of memory where your programs create objects on the fly. That is not what we are talking about today. We are focused squarely on the heap data structure, which is this highly organized, super efficient, tree-based structure.
So what exactly is this thing? Well, the entire concept, the whole shebang, it really just boils down to one simple, powerful principle. A single golden rule that dictates everything it does and makes it so useful.
And that golden rule is called the heap property. For a min-heap, which is what we'll be looking at, it means two things. First, any parent is always smaller than or equal to its kids. That's a guarantee that the smallest item in the whole collection is always right there at the top, ready to go. Second, and this is super important for later, it has to be a complete binary tree. That just means it's filled up from left to right, no gaps allowed.
And here you can see that rule in action perfectly. Look at the root node, the number 4. It's the smallest value in the entire tree, right at the top. Now pick any other parent. See the 5? It's smaller than its children, 15 and 6. The 8 is smaller than 16 and 20. This holds true all the way down the tree. That's the golden rule, right there.
So we have this logical idea of a tree, but if we actually built it with nodes and pointers and all that, it'd be kind of slow and a memory hog. This brings us to the absolute genius of the heap. There's got to be a smarter way to do this, right?
Yeah, exactly. How in the world do you represent this branching, hierarchical tree structure, but use a simple, flat list, like an array, and do it without losing any of those precious parent-child relationships?
And here is the big secret. The tree is just an illusion. Under the hood, a binary heap is nothing more than a simple array. That's it. All that complex tree logic, moving up to a parent or down to a child, it's all handled by a tiny bit of clever arithmetic. No pointers, no complex objects, just an array. This is what makes it so unbelievably fast and memory efficient.
So here's the first part of our map. If you're at any given node, at any index I in the array, you can instantly find its left child. The formula is always 2 times I plus 1. Simple as that.
And you guessed it, finding the right child is just as easy. Its index is just 2 times I plus 2. With these two simple formulas, we can traverse down our imaginary tree from any node we want.
But what about going back up? Yep, we can do that too. The parent of any node at index I is located at the floor of I minus 1 divided by 2. So with this complete little map, we can treat a plain old array as if it were a complex tree. Pretty cool, right?
Okay, so we've got our map for navigating this tree in an array. But what happens when we add new stuff or take things out? How do we keep that golden rule intact? This is where the action happens, with 2 key moves: bubble up and bubble down.
When we insert a new element, we do the easiest thing possible. Just stick it at the very end of the array. But of course, this probably breaks our heap property. So we do something called a bubble up. We look at the new element, compare it to its parent, and if it's smaller, we swap them. And we just keep swapping it up the tree until it finds its rightful place and order is restored.
Now, getting the minimum element out is a bit different. We grab the root, we know it's the minimum. But that leaves a hole at the top. To fill it, we do something that seems weird at first. We take the very last element in the array and move it all the way to the root. Now our heap property is totally broken again. So we perform a bubble down. We compare this new root with its children, swap it with the smaller one, and just repeat that process, letting it sink down until it settles into its correct position.
So, why do we go through all this trouble with arrays and bubbling up and down? Because this simple, elegant implementation makes the heap an incredibly efficient engine for managing priority. This isn't just some abstract tool for sorting. This is the core mechanism behind some of computing's most critical tasks. And this right here is the big payoff. the performance. Just looking at the minimum element, that's instant. It's always at index 0, so we call that O of 1 time. But here's the magic. Adding a new element, or removing the minimum, takes O of log n time. That is phenomenally fast. It basically means that even if you have millions of items, adding a new one or fixing the heap after a removal only takes a tiny handful of steps.
And that incredible efficiency is why heaps are absolutely everywhere. They are the textbook way to build a priority queue. And remember our question from the start? Finding the shortest path in your GPS uses Dijkstra's algorithm, which needs a heap to constantly prioritize which path to check next? Your computer's operating system uses a heap to decide which high-priority task gets the CPU. Huffman coding for data compression, it uses a heap to build its encoding tree. The heap is the silent, super efficient workhorse running behind the scenes of all of them.
You know what I love about the heap is that it's a great reminder that sometimes the most powerful solutions aren't the most complicated ones. They're the simple, clever ideas that get the job done with true elegance and efficiency. And it really makes you wonder, what other brilliant solutions are out there just hiding in plain sight? Thanks for watching.